Hello students. So in this lecture we shall discuss about the transport of electrons in nanoscale devices. Now, for efficient transport of electrons in these devices, we want these transport to be as collisionless as possible. Now, so collision is a problem, so we don't want that collision. So if the electron is being transported without collision with other electrons, then the motion is called a ballistic motion. However, if it undergoes collisions, and the electron rather drifts, then the motion is called a diffusive motion or diffusive transport. So we shall discuss between these two transport phenomena. Now, if the electron moves in a material in different paths like that, then the distance traveled by the electron between two collisions, these deviations from non-linearity, they are indicating collisions. Let us put them as red signs. So it seems that in these places, electron has undergone collisions with electrons, and that has caused a change in its path. So if we take the average length of the electron to be traversing between two collisions and as L, so that becomes the mean free path of the electrons. And we assume that the typical speed with which the electron traverses is, let's take it as a Vf. Now, on scales which are short compared to L, that means scales which are less than L, we expect that the motion, or we say that the motion is ballistic. As we have previously mentioned. And however, if the scales are greater than L, that means there has to be some collisions, then we say that the motion is diffusive. Now, the Drude has given a very good model based upon this diffusion motion of the electrons. He said that after the diffusion, when the electron is undergoing certain diffusion, so what actually did he said that the electrons is under the action of, say, an electric field E, and so this electric field will cause drift in the electrons. So drift velocity Vd is equal to Qe tau. So Q is the charge, is the electric field, m is the mass, and tau of course is the time, the collision time that is taking place. So due to this drift velocity, the resulting current density will be J equal to N 3D. This is the density Q into Vd. So we put the values of Vd here, so it turns out to be N 3D Q square E by M into tau. So we can write J. So we can actually find out the root conductivity. So we take out root conductivity sigma is N P square tau by M, and it is basically because J is equal to sigma E. So this is the root conductivity, and the mobility mu is equal to Vd by E. So that is again equal to Q tau by M. So if you again put the value of mu here, so we ultimately come up with this is then equal to N Q into mu. So according to root, conductivity is given as N, that's electron density, into electronic charge into the mobility of electron. So the formula of term in the case of root. Now if we again look into the mobility part, that means how efficiently the electrons are moving through the device. Vd by E is equal to Q tau by M, and it is expressed in centimeters square by volt second. So it may be extracted from low temperature conductivity measurements, because increase in the temperature might cause agitations in the electrons. So extracted from low temperature measurements because at high temperature there will be electron scattering, or we can call it electron phonon scattering may take place. So that is why we prefer to extract the value of mobility from low temperature, at low temperature. And as you can see, this mobility mu is directly related to the scattering time tau, and therefore mu is also therefore this mu is also the measure of material cleanliness. Now to come to some typical values, then for example in a single crystal silicon, at say 300 Kelvin, the value of mobility is 1000 centimeter square per volt second, and the scattering time is 2 into 10 to the power of minus 13 seconds, and the velocity of the electron is 10 to the power 5 meter per second, and mean free path is around 20 millimeters. Sorry, 20 micrometers. Whereas in the case of gallium arsenide, the mu value at the same temperature is 10 to the power 7 centimeters square per volt second, and its scattering time is 10 to the power of minus 10 seconds. It's a little more, and it crosses water and it will lower the mean free path of 10 to the power 5 meters per second. This is actually the same as in this case, and the mean free path here is 40 micrometer. Now we talk about diffusive regime. That means we have we understand that the electron will be undergoing some scattering. Okay, so in this case, the electron's path, the random path of the electron, this it will be given by a random walk model. In diffusion theory. Now, according to random walk model, what we consider a drunk man. This drunk man, he can actually take this man can take, say, n steps, each of length L. Now, whether he will take it in the positive direction, in the forward direction, or in the backward direction, that is why we associate a probability with it, that is 1 by 2. Okay. So, if we consider mathematically, that Pmn, this is the probability that a person is at point, the person is at M after he has taken n steps, each of length L, then that is equal to 1 by 2 the probability for each step, whether it is the forward or backward, to the power n, because he has taken n steps, into a quantity Wm, and Wm is simply equal to n factorial into half n plus m factorial into half n minus m factorial. Now, after performing all these operations for the calculations, the probability that the person will be at distance x after n steps is pxn, and it is equal to 2 pi L square to the power 1 by 2 into n multiplied by to the power minus x square by n L square, and this is nothing but the normal Gaussian distribution function, especially due to this factor. So we assume that the electron in diffusive motion is going through a random walk, and the diffusion constant d is equal to 1 by d VFL and it is also equal to 1 by d Vf square L, because we have square tau simply because of the fact that Vf the velocity is nothing but the distance traveled, that is L divided by time. So we can replace L by Vf into tau, so that is what has happened. So this is the value of the diffusion constant, and this d is basically denotes the dimensionality. So it is significant because of the fact that if we say that the device or the length or the material concerned where this electron transport is taking place is of the dimensions length, width and thickness. So dimensionality will be 3D if all length, width and thickness are greater than are much greater than the mean free path. It will be two-dimensional if the length and the width are greater than L, whereas the thickness is less than L, and it will be one dimension if only the length is greater than L, whereas the width and the thickness are less than L. Now, the way the electron gets scattered, basically there are two types. So, there are two types of scattering that is taking place. One is called specular scattering, and another one is called diffusive scattering. The difference between these two is specular scattering only takes place at the boundaries. So it will be like this. Electron will come and get scattered from the boundaries. It is we consider a smooth surface here. Then there is no randomization, no of momentum. And it has no effect on the mean free path. So this is what is specular scattering is all about. The diffusive scattering, on the other hand, takes into consideration the scattering with other electrons. So it will be more like this, not a very smooth one, but this is how it should be. It gets scattered from other electrons. So it is assumed that the surfaces are rough and it randomizes momentum. It will be P, and it definitely will reduce the mean free path L. So the effective mean free path 1 by L effective is again equal to 1 by the original mean free path plus the width. So this will actually reduce, this will actually also cause a change in the root model that we predicted. So in the root model we predicted that the sigma, sorry, not this one. In the root model we predicted that sigma is equal to NQ mu. So the new sigma, due to this consideration of this effective mean free path, so we will have a new conductivity also. So we call it sigma FF, and it will be just the ratio multiplication of the original conductivity and the ratio of the width and the mean free path. Now, the classical theory of electrical conduction issued the effect of conductivity and mobility, and there is rule of scattering. There is a semi-classical model of conductivity. So we consider, we move on to a semi-classical mode, and it was given by Fermi. So According to Fermi, when there is no applied field, it can be magnetic or electric. When there is no applied field, then there is the momentum of the electron. The momentum of the electron can stay between momentum of the electron can be minus p or plus p. So what we do, we draw a Fermi circle. That means take the ky and the kx value, and we draw a Fermi circle. And it is based upon the fact that P is equal to H cross K. So that is why there is a random thermal motion that is taking place. So this is the Fermi circle. That means the electron actually cannot pass through this Fermi circle. It has to stay inside this Fermi circle. So there will be a Fermi velocity corresponding to this Fermi circle, and that velocity will be Vf. It will be H cross K by M. M star here is the effective mass of the electron. And for copper, it has been found that for copper, this F has been found to be equal to 1.57 into 10 to the power 6 meter per second, and application of a magnetic field. Now this is with no magnetic field. Now what we are doing, we are applying a magnetic field. So the magnetic field will, as we have seen, that due to magnetic field, a drift velocity arises. So there will be a shift of this Fermi circle in the positive direction. Suppose the electric field is applied in this direction, so it will actually shift like this. There will be a shift, and this shift also indicates a shift in momentum, and the velocity will also be drifted. So apart from the free velocity, when there is no electric field, there will be a drift velocity added to it, and this drift velocity, so the net velocity V will be Vf plus Vd. Now, in this model, we also assume that the electrons on application of this applied field will also undergo collisions. So the length traveled before a collision within the lattice. So assume that length traveled before a collision within the lattice assume that is Lm, and it is now equal to the total velocity Vf plus Vd that we discussed, multiplied by the scattering time tau, and this is effectively, we can say it is equal to Vf tau, because this jet velocity is very low. So, and it turns out to be equal to 3.9 into 10 to the power minus 8 meters. That is approximately 39 nanometers. Now, the lattice constant in the crystal, there are the order of Armstrong, that is 10 to the power minus 10 meters. These are the lattice constants. So there are a lot of lattice constants. Now compared to so it will actually cause no frequent collisions. Whereas the thermally derived mean free path is order of 2.8 into 10 to the power minus 9 meters, that is 2.8 nanometers, which is quite less compared to this drift. So which is so due to this we will have more frequent collisions. So it is suggesting something. What it is suggesting is that due to this application of this electric field and due to the shift involved in the Fermi space, we are actually avoiding some collisions that would have normally occurred in electron transport. Now, let us come to a practical example of carbon nanotubes, CNTs. In carbon nanotubes, there are two pi bands. So it is like this shape. So this is a pi and this is a pi band. So there are two pi bands, and lowest resistance, this is called Landauer's conductance, G, lowest possible resistance is given as 2 e squared by h into n, depending upon the number of carbon nanotubes present, and the mean free path is order of 1.5 micrometers. And usually this R will be the reverse of that, so it will be H divided by assuming there are 2 pi bands, so this n is equal to 2, so it forms 4 e squared by h, and R is again h by 4 e squared. Now if we increase the length of the carbon nanotube, CNT length, it gets increased, actually there will be effect in the mean free path, effect in the resistance offered to the electrons in the carbon nanotube. So the new resistance R will be equal to h by 4 e squared plus the ratio between the mean free paths. Where Lm is the ballistic mean free path, and L is the original mean free path. Now, what happens when we apply a magnetic field? So there is always electric field present. On application of a magnetic field, as you know, it can produce an Hall effect. So this is the motion of the electron, say V. So apply a electric field is already present. We apply a magnetic field as well. So 3 of them are perpendicular to each other. So a Hall effect will be generated, and then we can write the equation based upon this Hall effect as mvd by tau is equal to E into E plus Vd cross B, the fourth equation. And due to this, we get different values. So writing it in different components, so we can have an Ex component and an Ey component. So they will be again related to some matrix values, and then Jx and Jy component. This is, you can represent in terms of matrix. So there will be different values of conductivity, since J is equal to sigma E. So E. So these are actually not conductivity. So E is equal to 1 by rho into J. So these are the resistivity values that one shall obtain. Now,